We've looked at the normal distribution and we've looked at binomials as two kind of core random variable concepts. I want to now look and see if there's any relationship between those two things and also be able to use some for more situations. So as a reminder, a binomial random variable deals with situations where there are strictly successes and failures. So it's a two-option situation. That's where the bi part of binomial comes from. There's a fixed probability of success. That fixed probability of success is P, and there's a fixed probability for failure. We call that Q. There's a fixed number of trials as well, N. We found that for a binomial distribution, the expected value is N times P, and the variance is N times P times Q. If I wanted the standard deviation, and I will, that's the square root of N times P times Q. The standard deviation will always be the square root of the variance. So here's an example, and we're just going to try what we know so far. I'm going to use GeoGebra a little bit to get some of these probabilities. But suppose that it's estimated that 40% of PCC students like Batman. I go out and I do a survey of 5 randomly selected students, and I ask them, hey, do you like Batman? X is the number of people that say yes in response. The first one, what is the probability that the third student is the first to not like Batman? Now, some of these situations that we'll run into are actually not binomial or normal. In those situations, we might be able to list out the probabilities though. So for example, on this one, the third student is the first to not like Batman. This would mean that I had the first person like, the second person like, and the third person did not like. If I can list out the probabilities and I can assume independence between trials, I can multiply these events together. This is just what the multiplication rule gave us, or what we got when we were using trees. So I'd have 40% times 40% times 60%. I'm going to figure out what this is in my calculator just so I have that number, but the process is the more important part. If order does matter, I do have techniques for dealing with that, trees and multiplication rules. Binomials in particular, they're more for these situations where I'm looking at exactly 3 people liking Batman, and I don't care if they're the first 3 or the last 3 or any combination. So I'm going to go to GeoGebra. And when I go into GeoGebra, I'm going into probability. And I'm not working with the normal model here, I'm working with binomials. And I am looking out of 5 individuals, so I'm going to change my N to 5. 40% like, so I'm going to change that P to 0.4. And I've got all of my probabilities showing up there on the side. In particular, if I was interested in exactly 3, it looks like there is a 23.04% chance of that occurring. No more than 3. Sometimes these no more, less than, at least phrases kind of trip me up a bit. So let's think about what no more than 3 means. And I typically do this just by testing numbers. So 0 is not more than 3. 1 is not more than 3. 2 is not more than 3. 3 is not more than 3. But 4 would be more than 3. So if I'm looking at for everything that is no more than 3, that really means 3 or less. So in my graph here, I'm looking at everything from 0 up to 3, and there's a 91.3% chance of that. Looking at this, it seems that the center of my graph is probably somewhere around here at 2 or so. Let's see if my formula matches up with that. So my expected value is the number of trials, so this is out of 5 people, times my probability of success. My probability of success is 0.4. That does give me an average of 2, just as it looks in that graph. Let's also find, it says the variance, but let's find the standard deviation instead. I'm going to take the square root of my n is 5, my p is 0.4, and my q is 0.6. So typing this into a calculator, I end up getting something like 1.0954 or so. And actually looking now at GeoGebra in this top left-hand corner, this is another way that I can verify these results. It's giving me my expected value and my standard deviation for this binomial graph. Part E, calculate the z-score for x equals 5. I'll do that, and I'll also determine if it's usual or unusual based off of that. To find my z-score, I'm going to take my value that I care about, subtract the expected value or the average or the center, whatever you want to call it, and divide it by the standard deviation. So in this case, my value is 5, my center is 2, and I'm counting by 1.0954 or so. I'm going to type this into a calculator and I'll see what I get. I'm getting something like 2.74 or so. Reminder, if your z-score is between -2 and +2, it's considered usual. If your z-score is outside of that interval, it is considered unusual. So I would say this is an unusual amount. So it would be rare to have 5 out of 5 students like Batman. There's only a 1% chance of that happening. So this is just kind of a recap of how binomials work in general. I want to try to visualize these things a bit. So what does this binomial 5 trials, 40% success rate look like? Well, let's just draw a sketch. And I'm no artist, I'm just doing my best. And sometimes that's all we can do. Okay, so my graph looks something like this. It's a little bit skewed to the right, but otherwise it's unimodal and symmetric. Looks like my average is 2, and my standard deviation is 1.0954. So my average is n times p. My standard deviation is the square root of n times p times q. Okay, let's say I'm looking at n equals 20. I'm going to change that here. And I'm highlighting the blocks just so it's easier for me to see the shape. Looks like unimodal, a little bit more symmetric this time around. Again, I'm just drawing a sketch to the best of my ability. I'm going to kick this up a notch to 100. Now, just a note, I'm a little bit concerned about my computer. Good. A little bit concerned about my computer when I was typing in that 100, because even though I'm not going through the process of calculating all of these things by hand, my computer's doing a considerable amount of calculations to come up with this. Just as a reference, try to think about making a tree with 100 sets of branches. That would be massive. It's a huge amount of calculations that we're asking the computer to do here. So I'm drawing a sketch, and I'm noticing that this is starting to smooth out. It was really kind of blocky to begin with, and as I get more and more blocks, I can kind of see the general shape of the thing coming to life here. In fact, if I squint my eyes, not even a little bit, if I put this red curve on top, this puts the normal distribution on top of the binomial, and they look very, very similar. So as my n increases, my graph looks more and more normal. For reference, let's go back to 5. Not a great estimate there. I have a lot of blank spots, and I have spots where it's sticking out. My initial graph doesn't look a ton like that normal distribution. But as I sample more and more, this thing will get smooth and start to look like this continuous distribution. I'm a little bit afraid to do this because I'm worried that I'm going to freeze up my computer while I'm doing a video, but I'm going to change this to 1,000 and see what happens. It doesn't even do, oh, there it goes, great. I was pretty sure I was going to brick my computer there, but it still works, but just barely. A little bit of a word of warning though. Did you see how it stalled and it looked like for a second I was about to crash my whole machine? I legitimately thought I was going to crash my whole machine there. So observations. First, as n gets big, my binomial distribution looks like a normal curve. My next observation, for really large n, technology might not work for binomials. I think this is kind of interesting because binomials are sort of my way of dealing with things when my by hand method doesn't work. So when my by hand method gets too hard to do, I use technology for binomials, but when my technology gets too rough for my binomials, I need a backup for my backup. And that distribution will be the normal distribution. When my computer starts to break, instead of worrying about that at all, I'm going to have a process where I can just find z-scores and look them up. So if it looks like a normal distribution, the only thing I need to know is how do I find the average and the standard deviation for binomials? Well, going back to the top of the page and thinking about this Batman problem, I found my average by doing n times p. So my center for these models, when I graph them, is going to be whatever n times p is. And my standard deviation will be the square root of n times p times q. This is called the normal approximation for binomials, and it links together my two big models that I deal with in Math 243. Let's practice this quite a bit together here to get used to this new formula. So I have the same thing written down at the top of this next page. The normal approximation for binomials states that for large n, my binomials look like this very specific normal graph. There are three assumptions for doing this. One assumption is I need to make sure I have a random sample when I'm collecting the data. In particular, I need to make sure there's no bias. If there's a clearly biased source that you're getting your information from, you probably shouldn't be doing any sort of statistical analysis with that. This is just a reminder. Also need to make sure that my probabilities stay the same in the trees if I'm looking at really large trees, and that's related to independence. The reminder, I have a backup for the independence rule, and that's the 10% rule. So if I sample a really small part of the population, I can assume that things are not related. So large enough that it looks normal, not so big that things start to affect each other. Finally, large n, I want to have 10 successes. You can think of those as being blocks on the left side or right side of your graph. So this is just saying I need at least sort of 10 things on both sides of my graph. 10 successes, that's n times p is greater than or equal to 10. And I want 10 expected failures. That's n times q is bigger than or equal to 10. So when I ask a question like, is n large enough? I'm checking if n times p and n times q are both bigger than or equal to 10. So here's a scenario. A student shows up to a 100-question true-false exam and knows none of the material. Let x represent the number of questions that they correctly guess. So random, let's assume that this is just, I'm guessing on each of the questions. I don't know for sure what I'm doing there. My guess on one does not affect another, so I have independence. And let's check if I have a large enough n to use this model. Starting out, I have n equals 100 samples. my probability of success is 50%. If it's true, false, I have a 50% chance of guessing that correctly. If 50% is my success rate, then 50% is also my failure rate. P plus Q should be 100%. Those things are complements. So let's check large N. I'm doing N times P. I have 100 times 0.5. That gives me 50. That's bigger than 10. I should expect to get at least 50 questions right. N times Q, I have 100 times 0.5. This is giving me 50 as well. I'm expecting to get 50 failures. What is the mean and standard deviation? Well, I expect to get 50 right, but actually sometimes I'll get less than 50 and sometimes I'll get more than 50. So my average, or my mean, is this N times P is this 50 number, but my standard deviation for how much that's going to vary is the square root of N times P times Q. In this case, I have the square root of N, 100, times P, 0.5, times Q, also 0.5. Doing a little bit of mental math, half of 100 is 50, half of 50 is 25, so this looks like that's the square root of 25. So I believe this gives me a standard deviation of 5. This tells me that my normal model will have an average of 50 and a standard deviation of 5. So how likely would it be for a student to get between 60 and 80 questions right on the exam if they just guess? Let's use this normal model now to answer this question. And I'm going to do what I do for every normal model. I'm going to draw my picture. This has two numbers. It's looking between 60 and 80. So I'm going to find my two z-scores, and then I'm going to look them up in the table. Drawing my picture, I have a center of 50, and I'm counting by 5. So this is 50, 55, 60, 65, and so on. In the other direction, I would have 45, 40, and so on. One of my values is 60, that shows up here. My other value is 80, that's going to be way, way off the charts, kind of rare. And I want the area between this. In other words, I want to know how likely it would be if I had 100 question true false to guess my way into getting anywhere between a D and a very, very low B, exactly at the B cutoff. So to find these z-scores, I'm going to take my value, subtract the center is 50, divided by the standard deviation. I type this into a calculator, 80 minus 50 is 30, 30 divided by 5 is 6. That's a z-score of 6.00. For the small value, I have value minus center over standard deviation. A quick look shows this is 1, 2 tick marks up, so I'm anticipating a z-score of 2. 60 minus 50 is 10. 10 divided by 5 gives me 2, just like I was hoping. I've drawn my picture. I found my z-scores. Final step here, I'm going to look it up. I'm going to have a large table value, and I'm going to have a small table value. Large table value. So I'm going to go to my normal table here. And I'm going to try to find 6.00. Now, looking at my z-score table, the largest possible number I have is 3.49 for a z-score. And that gives me a table value of 0.9998. This table value for 6 is going to be even bigger than that. So let's call that 0.9999. If it's off the table, use the best possible thing that you can and adjust it just a tiny bit. All right, 2.00. Well, this will be in the table. It's going to be in the 2.0 row and the 0 column. So 2.0 meets the 0 right here at that number of 97.72%. If it's between two values, to find the probability that it's between 60 and 80, I'm going to take the large table value and I'm going to subtract the smaller table value. And when I do 0.9999 minus 0.9772, I believe I get 0.0227. In other words, there is a 2.27% chance that a student would get between 60 and 80 on their next exam if they just guessed. Let's pull up GeoGebra and see how close that actually is if I'm dealing with a 100 question true false, 50% as my success rate, and it's between 60 and 80. So I thought it was 2%. It's actually 1%. I'm within 1%. That's reasonably close. And if you're wondering, why am I even off a little bit? Do you see these blocks, how they stick out of the graph just a tiny bit? This process is going to give me fairly good estimates, but the binomial model itself is always going to give me my exact values. So if you're wondering, why would I want to estimate at all? Just a reminder, when I tried to type in 1,000, I almost broke this computer here. So this is fine if you're dealing with like 100 for your n, but as soon as you get to really, really large values, say, for example, 200,000, you can't rely on technology anymore. So this is still giving me a very reasonable estimate, all things considered. Let's look at another example. So a study determines that about 4.2% of all post-surgery patients develop a surgical site infection. Suppose that there are anticipated to be 200,000 surgeries in the Pacific Northwest area next year. Let X represent the number of patients that develop a surgical site infection. Is N large enough to use the normal approximation? Okay. I'm checking if N times P is bigger than 10. And I'm checking if N times Q is bigger than 10. I'm dealing with 200,000 as my N. So I mean, yeah, probably both of these things are going to end up being bigger than 10, but let's check. My success rate, and success is the thing that you are counting. It doesn't mean that it's a good thing, is 4.2% for my infection rate. And for those not getting infected, that's 1 minus their complements. That'll be my 95.8%. So I'm going to multiply this by 4.2%, and let's see what we get. I just want to make sure that this is a number that is going to be bigger than 10. And when I do this, I get 8,400. So I expect 8,400 people to develop a post-surgical site infection. 200,000 times my Q, 0.958. This is the larger of the two probabilities. So if this thing was bigger than 10, this thing is definitely going to be bigger than 10. But I'm still going to type it into a calculator just so I can get that practice in. And I get 191,600 as my answer there. Just as a quick observation, if you added these two numbers together, you would end up with that 200,000 number. this is true in general. When you add together your n times p and your n times q, these should add to your total number of samples n. So is my sample size large enough? Yes. Both n times p and n times q are bigger than 10. What is the mean and standard deviation for x? So the mean, or my average, is n times p, and I already did that up here. I am expecting 8,400 people to develop one of these post-surgical site infections. As for the standard deviation, that's the square root of n times p times q. So that's going to be the square root of 200,000 times p 0.042 times q 0.958. I'll type that into a calculator and I'll see what I get. I got 89.71 or so. So this tells me the distribution for the number of infections that I should expect for this region should be about a normal distribution. I have a really large n with an average of 8,400 and a standard deviation of 89.71. Follow-up questions that I can now answer. So let's suppose that I'm wondering, would it be unusual to have 8,540 individuals with post-surgical site infection? So maybe they have supplies for dealing with this, and they're wondering, are we in good shape for handling what could happen to us this next year? Well, let's check it out. It also asked me, how likely would it be to have 8,540 or more? So let's answer that second question, and we'll get the answer to this one on the way. So I'm looking at 8,540 or more. I'm going to draw a picture. I'm going to find my z-score. And then I'm going to look that z-score up in my table. Drawing my picture, just as a rough guide, my center is 8,400. And my standard deviation is really close to the number 90, so I'm going to be counting by 90, 8490, 8310 or so. And my value is 8,540. That's about here. And I want that much or more. I'm noticing that it's shaded to the right. So when the time comes to find my probability, just a reminder, I find probabilities that are shaded to the right by doing 1 minus the table value. Let's find the z-score. I'm going to take the value that I'm concerned about, 8,540. I'm going to divide this by my standard deviation, and I'm going to subtract my center. So I have value minus center over standard deviation. I'm typing this into a calculator. And this gives me approximately 1.56 as my standard deviation. So I'm going to go to a normal table and I'm going to see where the 1.5 meets the 6. So I have 1.5, I'm going to the 6th column, and at that spot, I have 94.06. It's shaded to the right, so I want 1 minus this for my answer. 1 minus 0.9406 is giving me an answer of 0.0594. So would it be unusual to get that many infections? No, it's usual. It's within 2 standard deviations. And I should expect it to happen close to 6% of the time or so. I want you to just notice, though, This is almost like I'm doing two different types of problems. I start by finding the average and standard deviation, treating this thing like this binomial distribution problem to find those numbers. Then I use that information inside of a normal curve to calculate z-scores and look them up, just like that lesson on the normal distribution. This is really just pulling those two things together. Let's look at another example. Two types of p's are being crossbred. And suppose that we're looking at 100 of the offsprings that are being made here. And X represents the number of plants that have wrinkled peas as opposed to smooth peas. And let's suppose that we're told that 50% should be wrinkle. And that must mean the remainder, the other 50%, are smooth. They believe the actual proportion of peas that are wrinkled is greater than what's being claimed. So we're going to test the claim and see if the p equaling 50% that they're telling me is actually a reasonable value. So for my hypotheses, null hypothesis, I have p is equal to 50%. And for the alternative hypothesis, they believe the actual proportion is larger, so I will have more than 50%. So if the claim is true, I should see the success rate of 50% or less show up. And if it's not true, I think it might be more than that. So the null and alternative hypothesis are establishing what it means for something to be fair and what it means for something to be not fair. Determine if we can use the normal model to approximate X. If so, determine the model. So here's what I'm going to do. Let's assume, for now, that the claim is reasonable. That is, I'm going to base my model off of the assumption that p is equal to 0.50 as they're telling me. And long term, this is what I'm going to be trying to do. I'm going to come up with a curve that's based off of the claim value that they tell me. And I am going to compare my data to that claim to see if it looks close or not close. So two things can happen here. It might be the case that they say it's 50% and my data is 51% or so. So it's super close to the claim. And if I'm in a situation where these two numbers are really close like this, I'm probably going to think that it's a fair or reasonable claim. Now let's say it's 50% and I'm way out here at 90%. I'm not going to be inclined to believe that claim anymore, and I might think that the situation is not fair. So when I say assume that the claim is reasonable, I'm only assuming it's reasonable for now. I have no reason to call this person a liar just yet. I'm going to go through the process, and then I'm going to use data to support me. So my model, I'm looking at X is normally distributed with the center of n times p and a standard deviation of n times p times q. And I can use this if n times p and n times q are large enough. Well, my n times my p, 100 times 0.5 is 50, so that's big enough. My n times my q is also 50, so I do have a large n, So I can use this model. Let's plug in our numbers. I am expecting it to be normally distributed. 100 times 0.5, square root of 100 times 0.5 times 0.5. I'm doing something a little bit different on this one. I'm finding both the average and the standard deviation inside of the notation for the normal distribution. If you prefer doing it separately like we did on the previous problems, you're welcome to do that, but you'll still end up getting the same result, which is an average of 50 and a standard deviation of 5. Suppose a gardener ended up getting 70 plants with wrinkled peas. Based off of your model, is this usual or unusual? How likely is it to get 70 plants with wrinkled peas or more, assuming the claim is true? Okay. We're going to draw our picture. We're trying to answer the question of how likely is it to have 70 or more wrinkled peas. I'm going to find a z-score, and I'm going to look it up in a table. When I'm drawing my picture, it's based off of the center goes in the middle, so my center here is 50. And I count by my standard deviation, so I'm counting by 5, so this is 55, this is 45, this is 60, and my value of interest is out here at 70. So they told me that it should be about a 50% success rate. It should be close to 50 out of 100. But I'm supposing that I got data way up here at 70 instead. Already I can see a disconnect. This looks like it's probably not a fair situation. Let's find the z-score and the table value just to make sure though. To find the z-score, I'm going to take my value. My value is 70. I'm going to subtract the center is 50, and I'm going to divide by the standard deviation of 5. So I have 70 minus 50, I have 20, divided by 5. I don't know why I'm typing this into a calculator. 20 divided by 5 is 4. I'm going to try to look 4 up on that normal table, but I already know that it's off the normal table because the highest thing I have is like 3.49 or something like that. So my table value is going to be something like 0.9999. Now my picture is 70 or more, it's shaded to the right. So my probability value or my p-value, the likelihood of getting my sample data or more extreme here, is going to be 1 minus this table number. And if I do that, that gives me 0.0001, a really small number. In fact, as a definition, we say something is rare if your probability value that you get from a problem happens less than 5% of the time. So it would be remarkably rare to see 70 success rates if they're telling me the truth. So what conclusion do you think we can draw about the claim that 50% of peas will be wrinkled? Well, I think they're lying to me. But I don't want to call anyone a liar outright because I could just have unusual data. So I'm going to be really careful with how I phrase this. So let's see. I'm trying to think lawyer speak-ish. I reject the claim that my success rate is 50%. So I don't buy into that notion. I'm rejecting that. And the reason for this is I have evidence. I don't believe their claim anymore. I'm believing my data. So I think it's not 50%. I think it's higher than 50%. I have evidence that the actual proportion of wrinkled peas is more than 50%. I've just tested a claim about a population based off of the sample. Technically, I've done something called a hypothesis test. There will be a video that looks at hypothesis test in a lot more detail, but I'm looking at the math, and it's really just a matter of coming up with the right average and standard deviation, finding some z-scores, and looking them up. Ultimately, being able to test claims and determine if something is fair or not fair is extraordinarily important to be able to do as consumers of research. So this is a monumentally important topic in statistics. In fact, in 244 courses, there are typically only two things that you do. You look at hypothesis test and confidence intervals. So this is a half of a very big picture of how to look at data.